Okay, I think it's time for the second talk of the day. So our next speaker for the day is Martti Karvonen with a talk entitled Inner Automorphisms as Two Cells.
Thanks for having me. Let me share my screen and then we can get going. I take it it's visible now. Okay, great. Yeah, so this is some joint work I've done with Peter Hofstra, and let me first give a brief overview of what we'll be seeing today. So first I'll start by discussing our starting point. So there is a abstract theory of inner automorphisms that works in any category whatsoever. And then we'll use this theory to promote these inner automorphisms into two cells, much like we usually think of, much like it's possible to think of the category of groups as a two category. Well, I mean, one way a category theorist would think of it is by saying that, well, you can think of groups as one object, groupoids, and hence, you not only have homomorphisms between them which correspond to functors, but you also have natural transformations. So explicitly, you then get the idea that the two cell between two homomorphisms is then given by basically an inner automorphism, so an element of the group, such that when you conjugate with it, you get the other homomorphism out. And now something like this can be done more generally, and we will discuss some aspects of the resulting two categories, mainly some, behavior with respect to two-dimensional limits and co-limits. And usually, as talks are often some kind of ads, I'll mention that I'm finally the stuff I talked about at last TT on a closely related topic on sort of inner autoequivalences, or a 2D version of the theory I'll start from. That's finally coming out on arXiv soon, whereas the stuff I'm talking about today is more in the works, so you'll have to wait for that. So let's start from these, how we abstract from the situation happening with groups. So if you have a element of your group G, then you can of course conjugate with it, and you obtain an automorphism of G. And usually people then call that automorphism an inner automorphism and leave it at that. But actually, if you remember the element, well, first of all, let's say your group was abelian, then any element whatsoever acts trivially by conjugation. This induced automorphism would always be the identity. So actually, if you really want to think of know also the element you're doing the conjugation with, you should use more data. And luckily, this element does give you a lot more data than just this only, than only the automorphism of the group itself. Because you actually get the automorphism of any group give along any homomorphism out of your starting group G. So if you take any homomorphism out of G, then you can conjugate by the image of this chosen element, little g, in the target group. And these homomorphisms you get all fit together nicely, so that they satisfy some kind of a naturality square. So the condition is this, that if you take any further homomorphism then out from your group H, and then you look at what happens if you first conjugate in H by f of G, and then you apply this further homomorphism, or you do the further homomorphism and then you conjugate by the image of G under the composite homomorphism. Well, they'll both coincide. And this can be captured then by saying that this data here is actually a certain natural automorphism. Namely, it's a natural automorphism of the projection functor from the slice category. So you can look at the category where your objects are homomorphisms out of G, and your morphisms are commuting triangles. And then this has a forgetful functor as a group, and this data up here can captured by saying that you have a natural automorphism of this functor. And then it's a neat result that states that actually this is the only way you can get natural automorphisms of the projection. So in fact, you can recover fully the original element of your group that was doing the conjugation, even if the group itself was abelian, say. And now this definition can be then abstracted and then implemented in any category whatsoever. So in some cases, people also consider the dual notion, but here I'll always be working with this covariant isotropy. So we get this functor from any category C whatsoever to the category of groups by taking an object of a category. Then you look at the slice, and you look at the projection from the slice to the underlying category C itself, and then you take natural automorphisms of this projection. And now this thing is functorial, whereas if you just send an object of a category to its automorphism group, that in general won't be functorial. So the way it works then is that if you have a morphism from A to B, well, then you have a map other way between the slices. So then you can whisker, if you have an automorphism here of this projection, well, you can just whisker it along this map here, and then you'll obtain an automorphism of the forgetful functor from the slice here. So explicitly, we just have the data that we had on the previous slide, except now things are objects in some category C instead of groups necessarily. So you have an automorphism for every homomorphism out of, for every morphism out of your base object A, and they should satisfy this naturality condition. And then the way this functorial action of this thing works is that, well, I mean, it's concretely is that you can think of having originally a family alpha F for each F, and now you sort of keep pre-composing by this chosen map G, and that's how you sort of move this natural automorphism further along a morphism out of A. And now the way I think about this is that, well, I guess there's two ways to think about it here. So one way to say that an automorphism of some object in a category is an inner automorphism if you can extend it to a family like this. But I also like to think of the whole family itself as some kind of a extended inner automorphism. And I often even blur the terminology and just think of both of these as capturing the idea of an inner automorphism of an object in a category. So I want to be proving, a brief aside on size before I go on to discuss examples. Well, in general, if you have a functor between large categories and you look at all natural automorphisms of that thing, there might be a proper class of such natural automorphisms. And indeed, one can cook up some examples where you don't actually get a small group, you get a proper class of automorphisms. And when this doesn't happen, we say that the category has small isotropy, so that this operation Z is in fact a functor to groups rather than the functor to large groups or something like that. A trivial case when this happens is, of course, when C is small. But there's a more interesting sufficient condition, which is the following. So if you have binary co-products and C admits a small dense subcategory, then that's enough as well. So in fact, for a wide class of examples that, categories you'd usually think about, this isotropy tends to be small, even if in principle it might be large for some other, perhaps more artificial example. And now this, actually, I want to explain, okay, I'll give a hint where this comes from. So if you have binary co-products, then these projection maps have left adjoints, you can just use the co-products to build that. And then the small dense subcategory then guarantees that you can, instead of, sorry, if you look at automorphisms of the projection, you might as well look at automorphisms of the left adjoint. And the left adjoint is always co-continuous. So you might as well look at automorphisms of it when you restrict to the small dense subcategory. And now you're looking at natural automorphisms of some functor with a small domain, and hence there's only set many of those. And that is not only convenient for the size thing here, it's actually a convenient way of computing these isotropy groups for various categories. So I'll list some examples, but I won't go through the computations. So if you just have, if your ambient category is a groupoid, then the group of inner automorphisms of some object coincides exactly with the group of automorphisms. If you look at the categories of sets or of groupoids or categories, then nothing interesting happens here. So the identity is the only inner automorphism in this sense. The more interesting family of examples is the one where it's always some kind of a conjugation going on, and you have some kind of underlying monoid there. So if you look at monoids, then the inner automorphisms correspond to conjugation by an invertible element of the monoid. In particular for groups, you get conjugation by elements of the group. For rings, you get conjugation by units of the ring. So here, I don't assume that the rings are commutative. I just want them to have, I want them to be unital, but not necessarily commutative. And for strict monoidal categories, you get the conjugation by a strictly invertible object. So an invertible element of the underlying monoid on objects. Now, of course, you might protest this last example and say that the more natural thing to do, I mean, for a monoidal category would be to take an object that's weakly invertible. So an object A such that there's another object B, such that A times B and B times A are both isomorphic to the tensor unit and not necessarily equal. And I agree, you'd be right. But to make that precise, you'd work with the two-dimensional theory of isotropy. That is not the topic of the talk today. If you just restrict to abelian groups, then there's only two kinds of inner automorphisms. There's the identity and then minus identity. So I mean, taking inverses. And finally, if you take, wait, no, there's two more examples. So not finally yet. So if you take sets with a chosen automorphism of the set, and you look at morphisms that commute with the chosen automorphisms, then an inner automorphisms are basically of a set are given basically by the, or the group of inner automorphisms coincides with integers. So if you have a set A equipped with some chosen automorphism F, then the inner automorphism of that set amount to doing F some integer amount of times. And if you look at the category of presheaves, well, then what you get is exactly the automorphisms, natural automorphisms of the identity on C, and pre-composing with one of those, or I guess whiskering with one of those, it then will induce automorphism of the presheaf itself. And that's exactly how these inner automorphisms work for in this final case. So now let's use these inner automorphisms to define what, give a notion of a two-cell. So in a sense, we're just taking literally how it works for groups and then just using the fact that we have this general notion of an inner automorphism to implement this. So if we have an ordinary category C and we have two parallel maps, we're just saying that the two-cell from F to G is given by a inner automorphism, or I guess an extended inner automorphism alpha, such that when you evaluate the alpha at the identity, so when you look at its components at B and post-compose that with F, then you end up being equal to G. And we can give these two cells further structure so that we indeed get a two category. So first of all, if you want to compose them one after the other, then you can just compose and multiply them in the group of inner automorphisms. And now for horizontal composites, well, in principle there's two ways of defining it, but they're equal. So in a sense, what we're doing is that we just whisker. I mean, you could read this diagram. I mean, think of it in two ways. So you could think of first having this two cell here on the left that you whiskered with K, and before that you've then done beta, or the other way around. But either way, you'll end up actually being in defining the same two cell. And this works always, at least in the sense that for any category C, you'll then get a two category in this way. So for groups, this is exactly the motivating example we started from. And similarly, a lot of the other conjugation examples work in a very similar way. So then I guess for rings, you then say that two ring homomorphisms, or I mean, there's a two cell between two ring homomorphisms if you can conjugate one by unit to obtain the other one, and so forth for the other examples of where we had this conjugation kind of flavor going on. For sets and categories and groupoids, we don't get any new two cells. For abelian groups, well, we have the identity two cells, of course, and then the other one we get is that we will always have a two cell from any morphism F to minus F. And actually, if one thinks true what happens for a groupoid, then you'll get a kind of a boring two category. So between any two parallel two cells, there will be a unique one cell. Between any two parallel one cells, there will be a unique two cell. And finally, two presheaves. If you have two natural transformations, so two one cells between presheaves, well, then they are isomorphic in this sense in the resulting two category, precisely when they differ by a natural automorphism of the identity functor on C. I'll mention some side comments. So in some situations, people think of or even define inner automorphisms by saying that, well, you first need to find the right two category to work in, and then you say that the inner automorphism is an automorphism of an object that is isomorphic to the identity on that object. And in this kind of viewpoint, or the one I'm talking about, this actually, instead of a definition, this is a theorem, or, well, a very trivial result, but still it's a result. So you can just show that an element, an automorphism of some object A can be extended to an inner automorphism, or I mean, can be extended to an element of this isotropic group, precisely if it's isomorphic to the identity in this two category you can build from C. Another remark is that, okay, sure, so you can make any category into a two category. Well, let's repeat this, and then maybe get a three category and a four category and so forth. But this really isn't worth doing. So this follows actually from the remark on the previous slide. So for groupoids, the two category, if you start from a groupoid and build a two category, then that's locally indiscrete. So similarly here, this two category one builds from a one category is, well, it's actually a 2-1 category. So we only have invertible two cells in it. And then if you apply it, the same construction to all of its home categories, then the resulting home 2 categories will be locally indiscrete, meaning that between any 2 parallel cells, there will be a unique isomorph invertible tree cell between them. So there's nothing very interesting going on there. So sort of the construction really stops here. And another thing one could do is to check what happens if you then take this 2 category and then look at inner auto-equivalences there using the theory I'm not talking about really today. Well, then in an appropriate 2-dimensional sense, there's nothing interesting happening there either. Now let's move to the topic of limits and co-limits in this kind of 2 categories. And now, I mean, given the audience, I think a lot of the people here will know this theory of 2-dimensional limits and co-limits, and probably even better than I do. But in case someone needs a brief recap, let me say something very informal and hand wavy here, just so that the rest of the talk is more enjoyable. So as a very rough approximation, limits and co-limits in 2 categories are kind of like in 1D. So the definition is something very similar. It's some kind of universal solution to some problem, but there's 2 important differences. I mean, there's many others on a technical level, but the ones to highlight here are the following. So first of all, when the diagram itself, or sort of the problem you want to solve universally, might involve 2 cells in its description. So for us, a particularly important kind of 2-dimensional co-limit is the co-inserter, which is defined consists of the following things. So you have 2 parallel arrows in some category, and now instead of finding a co-equalizer that would make these arrows equal, you universally get a 2 cell between these by first post-composing with some map C, and then there should be some 2 cell between the composites, and it should be universal as such. Namely, if there was any other one, then it would factor uniquely through this. And the other difference is that, well, on a formal level, we're really saying that there's a isomorphism, or if you're working with a weaker notion of a 2 limit and equivalence between home categories, but concretely one can package this idea, into 2 statements of what the universal property means, so that they have a 1 and a 2-dimensional aspect, where the 1-dimensional thing says the sort of usual thing, at least if the shape is nothing funny. So for example, saying that something is a product in a 2 category, we're saying that maps into the product correspond to pairs of maps, so 1 to A and 1 to B. But then there's also the 2-dimensional property to check, which then says also that if you have 2 maps into a product and a 2 cell between them, then that's exactly the same thing as a pair of 2 cells between the 2 maps you get, 1 to A, to A and to B respectively. And another example I'll mention as a concrete case, because this is something that's one of the motivating examples. So if you look at how group theorists usually define something called H&N extensions, so Higman, Neumann extensions, I believe, they usually give an explicit construction. And the idea is that you have, the way they describe it is by saying that you have a group G, and you have 2 isomorphic subgroups of it, and some chosen isomorphism between them. And then you explicitly build a larger group where these 2, in which this original group G embeds or maps into. And moreover, these 2 subgroups you started from are now conjugate, and not just, not only they're isomorphic subgroups, but they're actually isomorphic via an inner automorphism of the larger group. And the H&N, but this H&N extension actually achieves a universal property. So it's sort of, if you achieved this construction in any other way, then the H&N extension would come with a unique map to it. And that actually amounts to saying that we have a co-inserter. So if you just have some H that's some subgroup, a subgroup of G, well, a category theorist would just say that you have a group H and then two monomorphisms to your group G. And then if you take the co-inserter in the two category of groups, well, then you'll end up exactly with the group that the group theorists call the H and an extension of this group along these two inclusions. And now these co-inserters play quite a important role, because they really end up saying capturing something important about the isotropic group of your category. And this will also play a role later in what kinds of other limits and colimits we have. So let's first assume that we just have finite colimits. Well, then it turns out that this two category can build from C has all co-inserters precisely if the isotropy functor is a representable functor, and if your category C actually was co-complete, then these conditions are equivalent to further saying that the isotropy functor has a left adjoint. So let's sketch the proof. So first of all, if you wanted to, if you had all co-inserters, then why is the isotropy group a representable functor? Well, if you just take the terminal object and take the co-inserter of this thing here, that's something that universally inserts a 2 cell between these two, in fact, equal 1 cells. But because this object is initial, then any object whatsoever there's always a map there, and any element of the isotropic group of that object A will always have any element of the isotropic group you can think of it as giving a 2 cell between the composites from the terminal object, initial object to your object A. And then by the universal property of the co-inserter, there will be a unique map corresponding to it from the co-inserter. But in a sense, that amounts to saying that, hey, elements of the isotropic group of A correspond to maps from the co-inserter to your group. And now the converse is perhaps more interesting. So if we take some object that represents it, and we actually choose a representation, which can then be, coincides, amounts to saying that we have some object R, and we have some chosen canonical inner automorphism of this object R, then we can use this object to build the co-inserter as follows. So first of all, we take the co-product of the codomain here. And now the image of this sort of universal inner automorphism is still and ends up being an automorphism of this co-product here. And then what we have to do is that we force this inner automorphism to take the composite when you first do F and then do the inclusion to the other map. So we sort of force it to be a 2 cell in the right way. And then one can check that indeed the image of tau under this inclusion is a 2 cell of the appropriate type. And one can then show that it's has the appropriate universal property so that you have a co-inserter. And for the final part, I'll just sketch it briefly. So if you have a left adjoint, then it's very, very easy to check that if you just apply the left adjoint to the integers, then you get a representing object. And on the other hand, if you have a representable functor from to groups from a co-complete category, then an old theorem by Freyd will guarantee that it will have a left adjoint. So let's see how this works in some of the examples we're discussing. So first of all, for groups, these functors are both kind of boring. They're both isomorphic to the identity. But this construction, or if you just unwind what happens in the course of the proof, you still recover the usual construction of the HNN construction. So the way it grouped here is constructed is by adjoining to H a new element T. So in a sense, you're taking the co-product of H with the integers, and then you add relations to force this new element T to satisfy this relation so that it sort of conjugates F to G. For monoids, this is the group of invertible elements as we discussed, and then the left adjoint is just the inclusion of groups into monoids. And for rings, we get the group of units, as I mentioned earlier, and now the left adjoint that is guaranteed by this theorem is the left adjoint people, of course, knew already that exists, but it's namely the group ring construction. But this game can also be played over algebras over any ring. So I think that's kind of a neat example of this. And now let's discuss some other two categorical properties of the resulting two categories. So now we'll assume that, we don't need all of these assumptions really here for all of these, but it's easier to assume more instead of try to be minimal for every statement whatsoever. But one thing that we want is that we have that the isotropy is representable, and then we can get some nice further properties. So first of all, any limit you already had in the underlying category is also a two categorical limit, so satisfies also the two-dimensional universal property. Co-limits also work, or at least connected co-limits work just fine. And then two other kinds of generally two-dimensional limits, co-equifiers and co-identifiers work as well. And finally, we have all tensors by any monoid whatsoever. So let's see how these constructions roughly go. So in the first case, we're just saying that some things that already were limits or co-limits in the underlying category are still limits in the two category. So we're saying that they also satisfy some two-dimensional universal property, and that's true. It just follows by a straightforward check. The main thing one needs to use is that this functor is representable, so that it's in particular it's continuous. If it's not, things could go wrong. But under these assumptions, we're good. Now the co-equifier. So I didn't explain earlier what co-equifiers and co-identifiers are. I'll just discuss briefly what happens with co-equifiers. So if you have two parallel two cells, then the co-equifier is sort of something like a co-equalizer, except now you're making two cells equal or in a universal way. So now if your isotropy is representable, then if you have two parallel two cells, well, the two cells are secretly elements of the isotropy group, which correspond then to two maps from the object representing this isotropy functor. And now if you take the co-equalizer of those two one cells, then that thing will turn out to satisfy the universal property of a co-equifier. And co-identifiers are built rather similarly if you know what they are. And I'll discuss this last case on another slide because it's kind of interesting. So again, we fix this representing object or this representation of this isotropy group functor. So first of all, you can just take the co-product of your object B with as many copies of this representing object as you need to go. And now these will all be, different images of this universal inner automorphism tau will always be inner automorphisms of this thing here. And then if we take a suitable co-equalizer of these, then we can force all these inner automorphisms actually to be maps from the sort of inclusion into the composite co-equalizer. And that's how you get the tensor of B with the free group on any set X whatsoever. So that's the starting point. So now we know that, okay, tensors by any free group exist. And now we use facts from the previous slide. So if you take any group whatsoever, you can always write it as a co-equalizer of free groups, and co-equalizers are connected colimits. So then, because we know that connected colimits play along nicely, then we can use the fact that, two facts. So first of all, that the inclusion from groups to categories preserves these connected colimits. It doesn't preserve other colimits. So in particular, the co-product of two groups in the category of groups is a very different thing than their co-product in cat. But for connected colimits, you won't see a difference. And now tensoring with some object is co-continuous in the group. So that means that the tensor of your object B with any group whatsoever G can then be obtained from by taking connected colimits corresponding to it when you first start this with it from these free groups. And finally, the part for monoids is nothing very interesting. It just comes from the fact that we are in a two category where every two cell is invertible. So functors from a monoid to a home category are the same thing as sort of what you'd get if you just freely made all elements of the monoid invertible and looked at functors from the group. So the universal property for being the tensor with some monoid is in this case the same thing as being the tensor with the corresponding group G. And now we also have some bad news. So in general, we can't assume or want all kinds of limits and colimits anyway. Or if we do want them all, then we must end up in a situation where actually we just had a locally discrete two category. So in particular, your binary coproducts will never be two-dimensional coproducts in this resulting two category. Your terminal object won't be two-terminal either, and you can't have equifiers, and similarly you can't find copowers by things that are anything. I mean, so in a sense, the result from the previous slide is tight. So we had tensors or copowers by a monoid, but if you take any category that's not a monoid, so either has no objects or more than one object, then you can't find copowers by those. So first of all, the easier direction is that, well, if all the isotropic groups are trivial, then then it's easy to see that you have a locally discrete two category, and then all of these limits have nothing interesting to say in dimension two. So in particular, they'll always exist. And I don't think I'll go through all the examples in all of these in the other direction, but I'll mention something. So let's see why the coproducts don't work in this case. Well, it's actually enough to think of just the coproduct of the terminal object with itself. Sorry, initial object with itself. So if you just think of the unique map to an object, well, what are two cells from that to itself? Well, they correspond to just elements of the isotropic group on X. And then if we have, if the coproduct did satisfy the two-dimensional universal property, then that would amount to saying that if you take any two elements in the isotropic group on X, well, then these are two cells from 0 to X. Well, then they have to actually come from a unique two cell from the sort of mediating map, but that will force these two elements of the isotropic group to be equal. I mean, for terminal objects, it's very similar. So two cells from, I mean, as in the previous slide. So if you just look at maps from the terminal object to X, and you look at two cells from that one cell to itself, then those correspond to elements of the isotropic group. And if we were saying that 0 was a two-dimensional initial object, then we're saying that there's only one of these, so that this isotropic group has to be trivial. And I think in the interest of time, I won't go through these other cases, but I'll mention one further thing, which also gives me a slight pause in this. I mean, in the sense that, okay, sure, for any one category, you can build a two category, but this construction, while interesting, maybe is not that greatly behaved. So in particular, it's not a two functor in any obvious way from cat to two cat. So for example, if you just think of the forgetful functor from groups to sets, well, there might be a two cell between them in the two category of groups, but there won't be a two cell between the underlying functions in set, because in general, I mean, this category set has no I mean, it's locally discrete, so there's no non-identity two cells there. So in effect, if you just take a functor between categories, then it's not generally a two functor. You need to give some extra data to promote it to such a thing, and you can actually characterize exactly what that extra data is. So if you had a functor between the categories and wanted to promote it to a two functor, well, the data you need to give is the following. You need a natural transformation from the isotropy on C to the composite where you first apply F and then take the isotropy on D. And it should also commute with the operation of mapping an element of an extended inner automorphism to just the automorphism at the base object. And using this, one can then check that, first of all, the isotropy functor itself is always a two functor, but some other functors, so for example, the inclusion of abelian groups to groups, you can't promote that into a two functor. And similarly, like argued in the previous slide, you can't promote the forgetful functor from group to set into a two functor. You can also build situations where there's more than one way of making a functor into a two functor. But there's also a nice sufficient situation where there's at most one condition. So if you have left adjoint whose right adjoint is faithful, then there's at most one of these. And then there's a further condition you can impose to guarantee that there's a unique way of making one of these left adjoints with a faithful right adjoint into a two functor. And class of functors that satisfy both of these properties is closed under composition. So there is a nice situation where you can, I mean, nice class of functors that you can always promote it to two functors, but unfortunately doesn't include everything. One can also play the same game for natural transformations, but I'll skip this part, I think, where it's starting to get time to conclude. So I'll just mention some further questions that I'd like to think about at some point. So first of all, well, instead of inner automorphisms, one could sort of play the same game and define inner endomorphisms by just looking at natural endomorphisms of the projection from the slice. And that's something you might call the isotropy monoid. And you can use that to build a two category now with possibly non-irreversible two cells. So you could study that thing. I'm not certain that that's really worth doing for two reasons. Well, first of all, I have some doubts already about the two category we just discussed. And then moreover, it's known that the sort of inner endomorphisms behave a bit more poorly than the inner automorphisms. So they're often harder to compute, harder to characterize, and often seem to be a bit less well motivated or interesting objects. So it's unclear if the kinds of two categories you'd get are anything people would really want to or need to consider. Another thing would be to just compute this situation in many other examples, further examples, see what happens there. And finally, I'm hoping that maybe people in the audience can suggest me some other two categorical issues to discuss here instead of just say limits and co-limits. And that's it for me. Thanks.
Thanks, Marty, for the talk. And now any questions is welcome. Let's thank the speaker, of course, and shoot any questions you may have. Pepe.
Hi, thank you, Marty, for your talk. Very interesting and inspiring to me. I have two questions. I hope that I catch the point. And I mean, I just heard things, so maybe I have to deepen before. But well, this is the question. First question: what is the relation with? I mean, when you speak about automorphism of the group you have inner automorphism, and then you have all the other automorphism. In fact, every automorphism can be seen as the inner automorphism in a bigger group, which is called the holomorph, which is the semi-direct product of the group G with the automorphism group of G. So this distinction may be overcome with this. So every automorphism is in fact inner somewhere. I was wondering what is the relation between your construction and the more general notion of automorphism of the group. This is the first question. And related with this is the following. I've always associated the notion of automorphism group with the notion of action, because you know. And so is there any link with this? I mean, in the category of group, you have this object, which is the automorphism group, which means that the actions are representable, strictly speaking. And so I was wondering if there was this link with action and with the representability of actions.
Yeah, thanks for the question. So first of all, for the first point that, so I guess you're right. So any automorphism of a group, you can sort of extend the group further, and then you get a nice square that commutes, where then the first you just have the automorphism, and then it ends up being inner on the larger group. I guess then in my setting, I'd kind of say that, okay, sure, but then that means that the automorphism you started from, it can't be sort of, it's not part of a two cell for any maps into your group G, but it will be part of, might be a part of some two cell into the larger group you build. So you still sort of plays a role when you need to keep track of your domain and codomain. And I guess similarly here, I'd say that sure, it's not the inner automorphism of the original group, but it's an inner automorphism of or some larger group. For the second question, so I haven't thought about this enough. So I like this. I've had some look where people have indeed studied more carefully in a different context this idea of a sort of or abstracted situation where for groups you have this, you can send a group to its automorphism group, and then it acts on your group. And there's this, people have studied this actual representability and stuff like this. I don't think there's a very straightforward connection, although I'd be interested in seeing one. So for me, I guess yeah, I guess there's still, you'd expect that there should be some kind of connection because the sort of inner automorphisms also, I mean, act on things. And now if the isotropic group is representable, then that sort of means that you have sort of this universal object with a canonical inner automorphism on it. And then that sort of is one way of trying to capture this action, but I'm not sure it really is talking about the same thing as what they're talking about when they talk about this action representability, but maybe there is some relationship. I'd be happy to look into that. Yeah, I mean, one thing that just came to my mind is that not only if you have this representing object for isotropy, it's always a co-group object when you think of, I mean, so there's a map from that object R to R plus R and so forth that make it into a group object in the opposite category. And I wonder if that's somehow related to this, you know, the kind of way it acts on objects.
Thank you.
Thanks for your answer. I think there's a question from Ivan.
Yes, so thank you for the talk. So I wanted to know if in the case of a topos, the isotropy group is still representable.
Yeah, I think so. I mean, yeah, so actually a lot of the stuff on isotropy starts, I mean, from works by Peter Hofstra and co-authors, and they've studied this carefully there. I've looked at it more on this sort of algebraic theory context, so I'm not as well versed there. But if I remember right, well, there's one difference though. So I guess, I mean, the way Peter phrases this is that he usually thinks that, okay, if you have a sort of algebraic situation, then you look at the covariant isotropic group like I did here. Whereas for a topos, he likes it, I mean, if you think of them more as sort of some kind of a spatial kind of notion, then you'd look at the contravariant isotropic group. And at least the contravariant isotropic group for any topos, I believe that is representable. And then that's a sort of a canonical group object inside the topos that somehow then captures inside the topos sort of the kind of information that this external functor does.
And do you know what's the object? Is it a simple object or it's a complicated one?
I think it depends on the kind of topos you take. I'm not sure. I know to say more at this point. Yeah. And
then I wanted to ask: is there, so you given a category C, you construct these two categories CZ. Does it have some universal property which is among two categories?
Yeah, so that's a great question. And I think there is so in some sense the answer is yes. So there's a way of, I mean, already, so there's a known result saying something about how the isotropy functor itself is somehow a canonical functor into groups. Roughly, the idea is that it's a canonical way of making the automorphism, I mean, fixing the fact that the automorphism group is not in general functorial. I mean, this hand wave, but there's a sort of corresponding characterization. So the idea is that there's a way of sending any object A to a group, but not only it's just a group, but you also have a homomorphism from this group to the automorphism group of the object you started from, subject to properties, and then isotropy functor is sort of universal in this way. I think it's the terminal one. And that characterization you can very much lift into then a characterization of the corresponding two category. So in a sense, it amounts to saying that it's a universal way of making C into a two category where the two cells are actually automorphisms in the original category in disguise.
Okay, thank you.
Thanks for your answer. I see a question in the chat by Matthias. Perhaps you want to ask it to the speaker directly, or I mean,
I'm fine with reading it here. Yeah.
okay.
So the question says, I mean, just to, so that it's also in the recording, someone's asking about the relationship between inner automorphisms of A in C and the inner automorphisms of A in the opposite category. So in a sense, that's asking about the relationship between the covariant and the contravariant isotropic groups. And I think in general, the answer is that they're not too nicely related. So you could have, for example, one might always vanish and the other one might be interesting. But there are some examples where they coincide. So for example, for groupoids, both of these just correspond to automorphisms of the object. Or sorry, for an object inside a fixed groupoid, they both coincide with automorphisms of that object. But I think, for example, for most of these algebraic theories, if you sort of look at the contravariant isotropic group, it doesn't really work as well there.
Can I ask one last question?
Sure, go ahead.
So of course, given this presheaf or co-presheaf, you can construct a two category. But is there any chance to construct a double category? And would this make sense in a way?
Yeah, no, that's a good question. So I think one of the earlier papers by Peter on this actually thinks of this as a double category, but then they actually, I mean, the sort of double category they build is basically exactly the same two categories discussed here. So it's just two category in disguise that you sort of happen to think of as a double category. I don't know of a version of this that would sort of, be genuinely double categorical, but maybe it's worth looking into. I'll definitely, yeah, have a think and see what comes up.
Okay, are there any other question? If not, we can thank the speaker again. And I suppose we can maybe stop recording now, whoever's recording, and whoever wants to stay here for a chat about math-related topics and whatnot. I think the call will be up for some time. So whoever wants to stay is welcome to. And let me just repeat that in the chat you can find the list of the speakers that are scheduled for this year. So thanks to everyone that participated to the event, and if you want to also participate to the next one, you're more than welcome, and you can find a list at the link which is in the chat. And also for all other related information, you can just visit the website.